I will present the third topic, nonlinear Schrödinger network. First, let's see where are we. I start with the physical principle of photonic time stretch and its governing equation, nonlinear Schrödinger equation, NLSE. Then, by focusing on the linear regime of NLSE, I have introduced the concept of fixel, which leads to the development of the phi-CV algorithms. By linear regime, I mean only the dispersion term in the NLSE is considered. Now, I will switch to the full NLSE to include other terms, especially the nonlinearity, and I will show how the physics equation can be used as an trainable model for AI applications. In this earlier work from our group called Nonlinear Schrödinger kernel computing, a hardware acceleration technique was proposed to bridge the latency gap between ultra-fast data acquisition in optical systems and machine learning inference on digital computers. It operates by modulating the input data onto the spectrum of a femtosecond laser pulse, and then propagating the pulse through a nonlinear optical medium. The nonlinear interactions governed by the NLSE in the medium will lead to a transformation of the data that makes it more separable by a simple linear classifier. In general, it uses NLSE as an analog computer in the optical domain. This reduces latency by orders of magnitude compared to utilizing numerical kernels like radius basis function, while maintaining similar accuracy. However, because the optical medium cannot be easily tuned, the performance is data dependent and limited by the unsupervised nature of the kernel. And overall, this technique has constrained flexibility due to its physical hardware implementation. Nevertheless, its underlying principles, particularly the use of nonlinear transformation from the NLSE to improve data separability, can potentially be adapted to full digital algorithms. In the full NLSE, due to the coupled nature of nonlinear and dispersive effects, deriving an analytical solution is challenging. In practice, the split-step Fourier method, or for short SSFM, is the most widely used approach to solving the NLSE. As its name suggests, SSFM divides the long propagation into multiple steps so that the dispersion and nonlinearity can be decoupled within each step, as demonstrated in the figure here. Mathematically, the effects of dispersion and attenuation can be represented by a linear transformation, while the optical curl effect can be represented by a nonlinear transformation. This structure resembles a single block in a common neural network, where a linear layer is typically followed by a nonlinear activation function. Inspired by this analogy, we propose a physics-based trainable model called nonlinear Schrödinger network. It treats each step of the split-step Fourier method as a Schrödinger layer, with the coefficients of the NLSE being the trainable parameters. By cascading several layers, we can construct a network that can learn nonlinear mappings from the input data to the desired output. With all the operations being differentiable, we can use backpropagation and gradient descent to optimize the trainable parameters. Look into one layer inside the network. It emulates the computational process of one step in SSFM, with D being the linear transformation parametrized by alpha and beta 2, and M being the nonlinear transformation parametrized by gamma. Each layer only introduces 3 trainable parameters, but they serve as a more efficient and interpretable parameterization compared to conventional neural networks, as we will demonstrate next. We compare our proposed nonlinear Schrödinger network against 3 different models as visualized here. The baseline is a linear classifier consisting of a single densely connected layer. MLP stands for multilayer perceptron, which is a feed-forward neural network with hidden layers and nonlinear activations. CNN is the 1D convolutional neural network that includes both convolutional layers and densely connected linear layers. In our nonlinear Schrödinger network, the input data is first zero-padded and then go through cascaded nonlinear Schrödinger layers. We add the padding for more accurate spectral representations during the computation. A max pooling layer is added at the end to mitigate the dimension increase caused by the zero padding. before going to the classifier. We have divided the model architecture into two parts, the embedding layers in the red dashed box and the final classifier. Embedding layers map the original data into a new space that is more separable, and the classifier makes the final decision of the classification. We compare the performance of our proposed nonlinear Schrödinger network with other models on time series classification datasets from different domains. The baseline results demonstrate poor performance, especially on linearly non-separable datasets such as Ford engine and the spoken digits. In contrast, our proposed nonlinear Schrödinger network significantly improves the accuracy by adding several nonlinear Schrödinger layers before the linear classifier. As the results reported here utilize 6 layers for all 3 datasets, there is only 18 additional trainable parameters compared to the baseline as highlighted in red. When comparing with MLP and CNN, our proposed method achieves comparable or better accuracy with way fewer parameters, especially for the embedding layers. All these results demonstrate the effectiveness of the proposed nonlinear Schrödinger network in capturing the complex nonlinear dynamics of time series data. In the meantime, it maintains a compact model size. More importantly, the trained nonlinear Schrödinger network can be interpreted as a virtual physical system that transforms the input data into another space for improved classification accuracy. These figures illustrate the learning curves of the nonlinear Schrödinger network trained on 2 datasets. As we can see on the right, the loss decreases while the accuracy increases for both training and validation datasets. They indicate the successful optimization using backpropagation and gradient descent. Also, the model can be implemented using mainstream deep learning frameworks with the auto-differentiation mechanism. We also present the convergence of the trainable parameters alpha, beta 2, and gamma in the first 4 layers during the training on one of the datasets. Initially, all parameters are set to 0. As the training goes on, these parameters gradually converge to values that optimize the classification accuracy. Finally, when the training is done, they can be interpreted as the properties of a virtual physical system that transforms the original data to another space for improved classification accuracy. We have also conducted an ablation study to investigate the effects of the linear operations D and the nonlinear operations N inside each layer. To do this, we first train the model with N only, and then we train the model with D only. These 2 models are compared with the baseline, which has only a linear classifier, and the full nonlinear Schrödinger network with both linear and nonlinear effects enabled. From the table, N only shows barely any improvement over the baseline, while D only achieves significant improvement over the baseline. The full model, however, have the best results overall. These behaviors can be explained by how we modulate and process the data. The input data is amplitude modulated onto the real input pulse E in. After propagation through the network, a complex output E out is obtained. Then its amplitude is fed to the linear classifier. When there's only the nonlinear operation, the self-phase modulation doesn't change the amplitude. That's why we don't see improvements for classification. When there's only the linear operation, all transformations are linear in the complex domain, except for the final step of taking the amplitude. This allows the linear operations to capture more underlying patterns in the data, which leads to improved accuracy over the baseline. When both operations exist, their coupled interactions in the complex domain enables the model to capture patterns in the data more effectively, which leads to the best results overall. This leads to the end of the 3rd topic, nonlinear Schrödinger network. As a conclusion and outlook, I've presented how to leverage laws from optical physics to craft algorithms in the digital domain. These algorithms have shown promising performance in vision enhancement in artificial intelligence applications while being efficient and interpretable. This diagram shows how physics initiates and connects different components of modern computing systems. We believe that physics-inspired algorithms represent a novel approach to bridging the gap between physics and algorithms, potentially driving innovations for new generations of computing machines that are more efficient and interpretable. Thank you.